For 2 million years it rained, not in storms, not in seasons, as a steady world-scale weather falling without pause across every shore of the only continent on Earth. To stand beneath that sky in any of those long generations, you would never have seen it stop. This is the story of that rain, of the world it found and the world it left behind. A planet older than memory, slower than imagination, and a single chapter in its long life when the air, for reasons no one alive could have understood, simply refused to dry. The time is 232 million years before our own. The age has a name now, given long after the fact, the Carnian. A small, technical word, attached by geologists to a thin band of rock that, for over a century, no one could quite explain. A red dryness underneath, a gray wetness above, and in between, the quiet trace of a transformation that took longer than any human civilization has ever lasted, several thousand times over. To understand what happened, the mind has to slow down, has to settle into a kind of patience that has nothing to do with calendars or clocks. 2 million years is not a long time in geological measure. It is, in fact, almost brief, a single line in the long paragraph of the Triassic. But to a planet, it is more than enough to redraw a coastline, raise a forest, soften a desert, and open a door to a new kind of life. The Earth has had many such doors. Most of them, no one was there to see open. The plants did not look up at the sky. The first dinosaurs did not understand the weather. They only lived inside it and were shaped by it, the way every living thing has ever been shaped by the air it breathes and the ground it walks on. So this is also a story about being held, about what it is for life to spend 1 million generations under a single, soft, persistent rain, about the slow grace of a world that will not be hurried, and that, even at its strangest, was already preparing the conditions for everything that came after. Time, in the deep past, has a different texture. The minutes a person knows, the seconds, the hours, the day from waking to sleep, these are creatures of a small life. They belong to a single body, in a single span. The Carnian belongs to no body. It belongs instead to the slow chemistry of the Earth's mantle, and to the long balance of carbon between rock and air, and to the patient way that water vapor rises, drifts, condenses, and falls. None of these processes hurry. None of them notice the passing of any single afternoon. They unfold across thousands of generations in steady, almost imperceptible curves. To stand inside such time, even for a moment, is a kind of rest. The clock that runs in the body becomes one of many clocks, and not the most important. The breath becomes briefly aware of the slower breathing of the planet. The inhale of carbon into rock, the exhale of carbon back into air, the long cycle that has set the weather of every age the Earth has ever known. The mind, which is so often hurried, grows still. The story has time. There is, in this telling, nowhere to be. And so, before the rain begins, there is space to settle, to imagine the long quiet of the world before the change, the dry winds across the center of a continent, the slow turn of the Earth, day after day, beneath a single set of stars that no human ever named, the fossils that have not yet formed, lying still in the bodies of animals that have not yet died. Everything, in this moment, is pre-rain. The world has not been told what is about to happen, and would not in any case hear. There is no urgency in this tale. There is no warning. The rain, when it began, did not announce itself. It came in slowly, the way fog gathers in a low valley before dawn, and once it had arrived, it stayed, for longer than any creature alive on Earth at the time could possibly have measured. It is a quiet story. It is, in some ways, the quietest story this planet has ever told, and it asks gently only one thing of the listener: to settle in, to let the centuries soften, and to listen to a rain that has long since fallen, but whose echoes shape the bones of every animal alive today, including the one breathing now in this room at the end of a very long line of survivors. To imagine the world the rain found, it helps to imagine, first, a single shape, a single piece of land larger than any continent that exists today, all gathered together into one. This was Pangaea, the all-Earth, the single supercontinent. Around it, a single ocean, Panthalassa, stretched across the rest of the globe, broken only by a long inland sea, the Tethys, that reached east into the heart of the land like a slow, warm finger. From orbit, if anyone had been there to look, the planet would have seemed strange. Most globes today are mostly blue, with land scattered across them like puzzle pieces. Pangaea was different. Half the planet, ocean. The other half, a single enormous mass of stone and sand and forest, almost 3 times the area of modern Africa. And inside that mass, deep within the interior of the continent, was the dryness. The cause was simple, in the way that planetary causes are often simple. When a piece of land becomes large enough, the rain cannot reach its center. Water rises from the ocean as vapor, drifts inland on the wind, and falls, and the further it travels from the coast, the less of it remains in the air. By the time the air had crossed thousands of kilometers of Pangaea's edge, there was almost nothing left of it to fall. So the heart of the world was a desert, not a small desert, not the kind of desert that appears today in a single country. A continent-spanning desert, wider than any modern landscape, broken only by lonely mountain ranges and salt-floored basins where, in the rare event of rain, water would gather and disappear within days. Red sandstones blowing in the wind. Slow, drifting dunes the size of small countries, moving year by year across a land that almost nothing called home. The light in such a place would have been hard. The sun stood high in a sky, almost always cloudless, and the air, dry as old paper, carried no softness in its glare. Shadows were sharp. The dawns and the sunsets, when they came, were brief. A few minutes of burning red across the western horizon, then night, with stars so cold and clear they seemed close enough to touch. The temperatures fell in those nights by tens of degrees from the heat of the day. A sandstone surface that had been hot enough to burn bare skin at noon would, by the small hours, be cool to the touch, the way a riverbed is cool, though no river had ever crossed it. The wind shaped the world. In the long centuries of consistent climate, it had built dune fields larger than entire modern nations. Some of those dunes climbed to heights of more than 100 meters and migrated steadily eastward across the continent's interior, advancing the way slow waves advance on a quiet shore. They overran older dunes. They buried in their slow march the few surface signs of the rare storms that had crossed them. They left behind, in the deep sediment, the long, sweeping crossbedding that geologists, hundreds of millions of years later, would read as a fossilized wind. In the few oases where groundwater seeped to the surface, life held on. Stunted seed ferns, small drought-tolerant relatives of the cycads, reptiles whose bodies were, in the way of all desert reptiles, conservative, small, low to the ground, slow-moving in the day, active in the cool of the dawn and the dusk. They drank dew, they burrowed, they were experts in the dry. The world, for them, had always been this way. In the rocks of this time, geologists today read that dryness in color. The sandstones are red. They are red because their iron is oxidized, exposed to air, weathered without much water to soften the chemistry. They are red the way old desert rocks are red, the way the cliffs of the American Southwest are red, the way the inner Sahara is red, the way Mars itself is red. A planet's surface slowly stained by air and time. Around the edges of Pangaea, life found softer ground. Coastal forests, river deltas, swampy shores where conifers and ferns and the early relatives of crocodiles lived. The Tethys margin was rich in places. Rivers flowed through valleys. Reefs of strange sponge-like organisms grew in shallow seas. There were animals that flew in early forms, small reptiles with stretched skin between their fingers, gliding from tree to tree. There were the first true mammals, very small, quiet, mostly nocturnal. There were many things alive, but the great interior was empty. And the climate, for 100 million years, had been settled into a single predictable rhythm. Extreme heat in summer, dry winters, monsoonal rains around the edges, but never reaching deep into the continental heart. This is the climate scientists later named the mega monsoon. It was an ordinary state for a planet with a single landmass. It had been so for millions of years before the rain began. It would have continued indefinitely if the deeper layers of the earth had not, at some quiet point, begun to move. The trigger, when it came, did not come from the sky. It came from below. Far out beyond the western edge of Pangaea, in what is now the Pacific, a great seam in the ocean floor began to open. The earth, in its slow internal geometry, had reached a moment when its mantle could not hold its heat any longer. A vast plume of warm rock, a column thousands of kilometers across, rising from somewhere near the boundary between the planet's mantle and its core, pressed up against the ocean crust, and the crust slowly began to fail. Geologists today call this the Wrangellia event. Its remains, scattered now across British Columbia, Alaska, and Yukon, were once part of an enormous undersea plateau, the size of a small continent in itself. For perhaps 5 million years, though most of the heat came in pulses with the most intense period falling within and around the Carnian, these fissures bled basaltic lava into the ocean, not in single eruptions, in long, sustained outpourings of a kind that no eruption in human memory has ever come close to matching. The lava itself was not the main event. The lava cooled. The lava, once cooled, became ordinary rock. What mattered was what came with it. Every cubic kilometer of basalt on its way out of the earth brought gases, carbon dioxide, sulfur, quantities that in a single eruption would barely register against the planet's atmosphere, but that, sustained over hundreds of thousands of years, accumulated. The atmosphere, during the early Triassic, had carried perhaps 1,000 parts per million of carbon dioxide. By the height of Wrangellia's activity, that figure had likely doubled, possibly tripled. The exact numbers are debated, the way numbers from such depths of time are always debated. But the broad shape is clear in the sediment, in the fossil leaves, in the chemistry of carbonates laid down across that age. The greenhouse thickened, the world warmed. Warming on its own would not have been enough. The earth has been warmer than this many times. What mattered was that the warming reached the oceans, and a warmer ocean, by simple physics, evaporates more water into the air. The atmosphere of a warm world is wetter than the atmosphere of a cool one. That extra moisture has to go somewhere. It rises, it cools, and eventually it falls. For the first hundreds of thousands of years of the Wrangellia outpouring, the change in climate would have been imperceptible to anyone walking the land. The rains around the coasts grew slightly heavier. The dry season softened a little. The deserts retreated, in places, by a few kilometers along their margins. Nothing dramatic. Nothing a single generation of any animal alive would have been able to feel as a turn in the weather. The kind of change that, in human terms, is not a story at all. It is only the slow background of a world settling into a new equilibrium. Beneath the ocean, the lava continued to flow. The fissures continued to open. The mantle plume, once awake, did not return quickly to sleep. And in the air, far above, water vapor gathered, lingered, and drifted further inland than it ever had before. The chemistry of the change is, in its essential outline, simple, the kind of chemistry a quiet evening can hold without strain. Carbon dioxide, released from molten rock as it cooled, mixed into the atmosphere. Each molecule of it, light and small, drifted high into the air and stayed there. Carbon dioxide, unlike water, does not condense into clouds. It does not fall as rain. It only lingers year after year, decade after decade, century after century, until the slow processes of the rock cycle, the weathering of stone, the burial of plants, the precipitation of carbonate minerals in the sea, pull it back down. In an ordinary century with an ordinary planet, those processes balance the slow leak of carbon from old volcanoes. In the Carnian, with Wrangellia awake, they could not. The leak, for many hundreds of thousands of years, was greater than the absorption. And so the atmosphere gradually thickened. A thicker atmosphere holds more heat. The sun's energy enters as visible light, warms the surface of the ocean and the land, and would, in a thinner air, radiate quickly back to space as infrared. Carbon dioxide intercepts that infrared, returns part of it downward, and the surface accumulates warmth. The mechanism is the same as the mechanism that warms a greenhouse on a cool day. It is the same mechanism that makes Venus, with its dense carbon atmosphere, hotter than Mercury, despite Venus's greater distance from the Sun. It is, in the long story of planets, an ordinary physics. It is also, in the slow accident of the Carnian, the mechanism that began to fill the air with rain. Around the equator, where the ocean was warmest, the change was felt first. Sea surface temperatures rose on the order of a few degrees. The trade winds, which had carried dry air across thousands of kilometers of continent, now carried air with more vapor in it. The high-pressure cells over the central interior of Pangaea, which had locked in the dryness for millions of years, began to weaken. The patterns of the global circulation reorganized slowly into shapes that no model from before the Carnian would have predicted. The planet was finding a new climate. It would take a long time to settle, and the rain, when it came, would come not as a single storm front, but as a quiet, distributed thickening of the entire global sky. There's no single moment when the Carnian Pluvial began. There's no afternoon, no decade, not even a clear century. There's only a band in the rock record where the color of the sediment changes. Below the band, the rocks are red. Old desert, iron, oxygen, dry winds. Above the band, the rocks are gray and brown and black, full of organic carbon, full of the soft trace of buried plants, the kind of sediment a river leaves behind or a swamp slowly fills. In some places, the boundary is sharp, no thicker than the width of a finger. In other places, it is gradual, smeared across a meter or two of stone. Wherever it falls in the world's exposed Triassic outcrops, the meaning is the same. At a certain point in the deep middle of this age, the world stopped being dry. Imagine a coastline, the Tethys side of Pangaea, somewhere in what would later become the Italian Alps. the slow shores of an inland sea, dotted with reefs lined with coastal forest. For a long time, the sediment on those shores has been red, sandy, sun-baked, washed in only by occasional storms. And then, year by year, decade by decade, century by century, the sediment begins to darken. Mud, plant matter, fine layers laid down by water that has come and stayed and not retreated. The grasses had not yet evolved. There was no green meadow, but the swamp ferns thickened, the horsetails grew taller. The ground, where it had once cracked open in the heat, was held now by roots and humidity and the slow accumulation of leaves that did not this season dry to dust. Walk inland in this time, and the change deepens. Where there had been dunes, there are now braided rivers, broad and shallow, crossing the old desert plains in 1,000 strands. The salt basins, which for tens of millions of years had been crusted, glinting in the sun, fill quietly with fresh water. Lakes appear that no one alive on Earth had ever seen the bed of dry. The wind, which had carried sand for as long as the continent had existed, now carries the smell of wet leaves. And from the sky, the rain. Soft, more than violent, not the brief hot downpour of a tropical storm, but a long, low rain, settling in for season after season, year after year. Sometimes heavier, sometimes lighter, sometimes broken by a few weeks of gray, lit cloud, but never gone. Never long enough to let the ground forget the wetness, never long enough for the dunes to return. In the high latitudes, the change was not the same. Where the world had already been wetter, the rain came as a thickening, a blurring of the seasons. The forests of southern Pangaea, in what is now Australia, in what is now Antarctica, took on a softer, mossier character as humidity rose. The lakes deepened, the rivers ran heavier and more often. There was no sense, anywhere on Earth, of a land suddenly drowning. Only a sense, slow and gentle, of a planet whose air had grown heavier with water, and that was finally giving that water back to every part of itself, all at once. For a long time, no creature on Earth knew that anything had changed. Each animal lived inside its own brief life. A reptile of the Carnian, in any of its many forms, would have been born under a damp sky, and would have died under one, and would never have seen a dry summer of the kind its grandparents had known. The world it inherited was already the wet world. The dry world had become history before it could be remembered. Only the rocks remember. The rocks and the slow chemistry of carbon and the soft dark layers of buried mud that, 230 million years later, geologists have come to read like a long, calm letter from a planet that, for a brief while, decided not to dry. The color change in the sediment, when seen up close, has its own quiet beauty. A field geologist working in a Triassic outcrop today, in the Dolomites or in the cliffs of the Bristol Channel, walks past several meters of red sandstone, the kind of stone that has been red for so long it almost seems to be its natural state, and then, without warning, the rock changes. The red softens to brown. The brown deepens to gray. The grain becomes finer. In the freshly broken surfaces, dark streaks of fossilized plant matter appear. The hammer rings differently against the stone, a slightly duller note, where the iron content has dropped and the organic carbon has risen. To the trained eye, even without instruments, the change in chemistry is visible. The world changed here. The desert ended. In some sites, a thin layer of dark, almost coal-like rock marks the moment most clearly. It is not coal in the formal sense. There were no peat-forming wetlands in most places of the kind that built the great Carboniferous coal beds, but it is rich, organic, dark in color, full of the fragments of plants that fell into stagnant water and never had a chance to decay. To find such a layer in a Triassic outcrop, where the surrounding rocks are otherwise dry-looking and red, is to find the trace of a long pause in the dryness. The geologist, kneeling beside the layer, sees in it the moment when a particular valley in this particular place became wet enough to hold its dead plants underwater year-round. The same kind of trace, in 1,000 variations, appears across the world. The rain, once it had arrived, settled in for a length of time that the human mind has very little practice with. 2 million years. Imagine, if it is possible, the entire span of human civilization from the first villages of the Fertile Crescent all the way to the present moment, and stretch it out end to end 200 times over. That is the rough length of the Carnian Pluvial, long enough for a coastline to migrate hundreds of kilometers inland and back again, long enough for a dozen complete cycles of orbital climate variation to come and go beneath the broader signal, long enough for whole groups of animals to evolve, spread, and quietly disappear while the rain continued. The evidence for the duration is written into the layers of the rock. Geologists working in the Italian Dolomites, in the Germanic Basin, in the rift valleys of what would become Britain and the eastern United States, in the great basins of South America and China, have measured the bands of pluvial sediment everywhere they appear. The thicknesses vary. The detailed timing varies, but the broad signal is the same. From around 234 million years ago to around 232 million years ago, a deep humidification reached almost every part of the globe. The sediment they measure is not random mud, it is paleosol, fossil soil, laid down by the action of living roots, decaying plants, weathering rains, percolating water. It is the kind of soil that does not form in a desert. It does not form in a few wet seasons either. It needs continual moisture, sustained for thousands of years at a time, before its characteristic chemistry takes shape. And in the Carnian record, the paleosols stack on top of each other, generation after generation, layer after layer, with no break, no return to the old dry conditions, for almost the entire 2 million year span. The chemistry of these layers tells the same story. Stable isotopes of oxygen, locked into the carbonate of ancient soils and shells, record the temperature and the rainfall of the world they formed in. Across the Carnian rocks, those isotopes shift and shift again and stay shifted for a length of time that almost no other interval in the Triassic shows. It is not a single storm. It is not a season. It is a planetary weather pattern settled in for longer than mammals have existed in their modern form. In the meantime, the surface of the Earth was changing. The deserts retreated. Rivers reorganized themselves, carving wider, more meandering channels through what had been wind-shaped plains. The interior basins of Pangaea, which had been sun-baked salt flats, filled with freshwater lakes and slow, organic, rich swamps. Some of those swamps in time became the coal beds of the late Triassic, the only true coal beds of that age, formed during this single window when the world was wet enough to bury its dead plants faster than the air could decay them. Around the coasts, the carbonate factories of the Tethys reefs began to falter. The shallow seas, which for millions of years had been clear and warm, and home to thick reefs of sponge-like organisms, were now flushed with mud. Rivers, swollen with rain, carried fine sediment far out into the ocean. The clarity of the water dropped. The reefs, which depended on light and stable chemistry, thinned. In many places they failed entirely. The fossil record of the late Carnian shows reef collapses across multiple continents, not a single sudden event, but a long, slow interruption, lasting as long as the rains themselves. And above the surface, the sky carried its long, soft labor. Day after day, the same gentle rain, the same low gray light, the same air full of water, cool against the skin of every animal alive in every corner of the only continent on Earth. The hydrology of such a world has its own quiet structure. A planet that is being soaked year after year develops a different set of flow patterns than a planet that is being dried. Soils, once they have absorbed enough water to become saturated, behave like sponges. They hold the rainfall of one storm into the next and release it slowly through seepage into the streams that drain them. In the long pluvial, almost the entire surface of Pangaea, away from a few high deserts that never quite gave up their dryness, became a saturated landscape. Every footprint of an animal in the soft mud filled within minutes with seeping groundwater. Every fallen leaf began to rot the moment it touched the ground. The rivers reflected this saturation in their own behavior. In the dry world, rivers had been narrow, deep-cut channels, draining the brief storms of their basins into the nearest sea. In the pluvial, with so much more water in the system, the rivers spread. They spilled across their floodplains. They left behind, in their slow seasonal cycles, broad sheets of fine sediment, layer upon layer, year after year. Geologists today read these sheets as the characteristic floodplain deposits of the Carnian. Pale brown, fine-grained, full of root traces, full of the organic carbon of plants that grew in the slow water and were buried beneath the next year's flood. Lakes formed in places where lakes had never existed. The interior basins of Pangaea, which had been salt flats for tens of millions of years, filled with fresh water as the rains continued. Some of those lakes became large, the size of inland seas, fed by rivers from every direction, fringed with conifer forests, walked by the tracks of long-legged reptiles whose footprints are still preserved, in places in the hardened mud of their shores. Other lakes were small, thousands of them scattered across the new landscape, each a small ecosystem of plants and animals settling into the wet conditions. The world had become, in a quiet way, a world of standing water. The dry continent had been replaced by a wet one. Among the animals already alive, the rain was not equally kind. The reptiles that had thrived in the dry world, the broad, sturdy plant-eaters known as Dinosaurs with their parrot-like beaks for grinding tough desert vegetation, had built their bodies for a different climate. Their teeth were shaped for fibrous leaves and seed ferns. Their physiology was tuned to long droughts, slow water, hot days. When the world softened, they did not soften with it. The plants they ate began to be replaced by other plants. The landscapes they had walked across changed shape beneath their feet. Their numbers thinned, their range narrowed. Within the span of the pluvial, they would, in many places, simply be gone. The same fate, gentler in its own way, fell on the Dinosaurs. These were the survivors of an older world, heavy, herbivorous, beaked, distantly related to the ancestors of mammals. They had outlasted the great dying at the end of the Permian. They had walked the dry interior of Pangaea for tens of millions of years. They had been one of the most successful groups of large land animals on Earth. And now, as the rain settled in, the open dry plains they had grazed gave way slowly to closed forest. Their food shifted. Their predators shifted. And though they would survive in scattered places for millions of years more, the height of their dominance was now behind them. In the sea, the long lineages of older reefs faded. Sponge-like organisms that had built reefs through much of the Triassic could not adapt to the muddier, fresher, more variable waters that the rains delivered. The corals that survived would, in time, give rise to the modern lineages, the scleractinian corals, ancestors of every reef alive today. But that lineage was small then. It was only a beginning. And in the swamps, in the slow, wet, plant-thick interior of the New World, something else was beginning too. Something that, at the time, would not have looked like much. A few small, lightly built reptiles walking on long hind legs with hollow bones and quick reflexes. They had existed before the rain began. They had been a minor group, scattered, rare. But their bodies, by accident more than by design, had been built for the kind of world the rain was now creating. They could move quickly across soft, uneven ground. They could thermoregulate well in cool, damp conditions. They were small enough to thrive on the new abundance of insects, the small early mammals, the seedlings of the spreading conifer forests. These were the early dinosaurs. In the first records of the Carnian, they account for perhaps 2 or 3% of the land vertebrates in any given fossil assemblage. They are present, but barely. By the end of the pluvial, in the same locations, in the same kinds of fossil assemblages, that figure will have risen to 20, 30, and in some places more than half. It would be wrong to say that the rain made the dinosaurs. They made themselves. Every group of organisms that survives a planetary change does so because the bodies and behaviors it had already brought to that moment happen by chance to fit what comes next. The dinosaurs had not asked for a wet world. They had not predicted it. They had only happened to be the kind of animals who could live in one. Small, fast, efficient, with the breathing apparatus and the bone structure that, in this new climate, simply worked. The planet does not choose its successors. It only opens the door. What walks through it is the result of every prior accident in the history of life, all converging on the moment when conditions, for whatever reason, change. It is worth resting for a moment on the gentleness of how the door opened. There was no catastrophe in the Carnian of the kind that ends an age in a single afternoon. There was no asteroid, no sudden burst of lethal volcanism, no hours of darkness across the whole of the world. The change unfolded across hundreds of thousands of years, and the animals alive at any given moment lived inside a normal-feeling life. They were born, they grew, they ate, they reproduced, they died. Their landscapes shifted slowly enough that no individual ever noticed the shift. Their food sources changed across many generations in ways that were felt only as the slow rise or fall of a population, not as any single event. For the rhynchosaurs in the late Carnian, there would have been no moment of crisis, only the slow narrowing of suitable food, slightly fewer of the seed ferns they liked year by year, slightly more of the new conifers whose leaves they could not chew, a drought that did not come, a swamp that filled in beside their old grazing grounds, a clutch of eggs in some season that hatched into juveniles who could not find enough to eat. The population thinned by degrees across many lifetimes. There was no last rhynchosaur in any meaningful sense. There were only fewer and fewer until in any given valley no more were seen. This is how most extinctions in the long history of the earth have actually felt to the animals living through them, not as a sudden ending, only as a long, slow narrowing. The catastrophes, the asteroid at the end of the Cretaceous, the great dying at the end of the Permian, are the dramatic exceptions. Most of the time, the world changes the way the Carnian changed. A long shift in conditions, a long redistribution of life, no single moment to remember, no warning to be given. only the eventual quiet absence in some valley of an animal that had once been there. Inside the long rain, the world's plants reorganized themselves first. The seed ferns of the dry Triassic, the broad, leathery-leaved species that had dominated the open lowlands for so long, began to disappear from the basins where the rivers now ran year-round. In their place came new conifers of forms that have, in the very deep family tree, ancestors of the pines, the cypresses, the araucarias of today. Their leaves were finer, narrower, more efficient at handling the steady rain. Their bark was softer, their seeds were lighter, dispersed by wind into the new open spaces. In the wettest valleys, the horsetails grew taller than a person, tall, hollow-stemmed plants lined in vertical green ridges that thrived where the ground was always damp. Their cousins still grow today in damp ditches and stream banks, but in the late Triassic they formed forests, dense and silent, where the only sound was the slow drip of water from one frond to the next. The ferns, ancient even then, took advantage of the new humidity. Tree ferns rose into the canopy in places where the old forest had been thin. The understory thickened. The world that had been open and dry under a hard sun became, for the first time in many millions of years, a green and shaded place across vast stretches of its surface. In the rivers, the new conditions brought new life into older forms. The temnospondyls, large amphibians, broad-headed, slow-moving, the descendants of much older lineages, found themselves in conditions that suited them more than the dry world ever had. Their populations grew. Their species diversified. Some grew to lengths greater than 3 meters, lying motionless in the soft mud of riverbanks waiting for fish or unwary land animals to pass. They had been creatures in the old world of marginal places. In the wet world, they were among the dominant predators of fresh water. In the air, the first true pterosaurs appeared. Their early forms had been small, awkward, gliding only short distances. By the late Carnian, the lineage had begun to spread, with longer wings, lighter bones, more efficient flight muscles. The wet, insect-rich air of the pluvial would have suited them well. Small, agile, hawking insects above the new lakes and along the long, slow rivers. And the ancestors of the modern crocodilians, in many forms now, lived in those rivers as well. Slim and fast, often more terrestrial than their descendants, they were the most varied land predators of the time. Some hunted on long legs far from water, others lay flat in the shallows. Almost all of them were adapted, in one way or another, to a world that had become reliably wet. It is a quiet picture. There are no great dramas in the surviving record. Animals were born, they fed, they died. The bones that reached the sediment were quickly buried under the next year's mud. The bones that did not were dissolved or crushed or scattered. Most lives left no trace. The few that did are scattered now in fossil sites across the world, in Argentina, in Brazil, in the rifts of eastern North America, in Britain, in southern Africa, in northern Italy. From these, scientists have been able to read with surprising clarity what kind of world the rain had grown. It was, by every measure available, a softer world, greener, cooler in the day, quieter in the way long rain is quiet. The deserts had not been forgotten, they had only been suspended, and every life inside that world lived under a single sky that, for as long as any of them could have known, had always been heavy with water. The forests of the Carnian, viewed from above, would have made a different mosaic from any forest of the present age. There were no flowering plants. The bright green of a modern broadleaf canopy did not exist anywhere. Every leaf in the world was either a needle, a frond, or a strap-shaped form on the seed plants of older lineages. The colors were softer, the greens deeper, more uniform, the textures, in close view, finer and more uniform than the leafy variety of a modern temperate woodland. Walking through such a forest, a person from the present would have felt the strangeness mostly in the silence. No bird song, because birds did not yet exist. No buzz of bees, because bees did not yet exist. No chorus of frogs, because the frogs of the time were quieter, less varied, fewer in number. The forest was alive, but it was alive in a different register. The sounds, when they came, would have been the slow drip of water from a frond, the soft splash of a small creature dropping into a pool, the creak of a high branch in a wind that, after months of gray weather, had finally begun to turn, the rare, sharp call of a flying reptile, distant and brief, and under everything, the long susurrus of the rain itself, falling for hour after hour onto wet leaves, into wet rivers, onto the long, slow surfaces of a soaked world. Time in such a forest would have moved at the speed of moss, the same view, day after day, the same patient drip, the same low light between the high canopies of the conifers and the saturated ground. There was no rush in any direction. The forest was not going anywhere. It was only being, the way long forests are only being, alive, awake, holding its slow breath of vapor and oxygen, asking nothing of the listener. The first true dinosaurs are scarcely larger than a medium dog. Eoraptor, Herrerasaurus, Saturnalia, names given long after they walked, bipedal, light-boned, fast, with grasping hands and small sharp teeth. They are not impressive. To stand near one in life would be to see an animal a person could carry in their arms or scare off with a stick. They were not the rulers of the Carnian world. They were one of its many guests. But they had something none of the other large land animals had, a body plan optimized by quiet evolutionary luck for the new conditions. Hollow bones, active metabolism, an efficient breathing system with one-way airflow through their lungs that allowed them to move and breathe and sustain effort in conditions that would have left the older reptiles panting in place. A grasping hand, derived from the climbing ancestry of their lineage, that was ready to be modified into many forms, into the speed-hunting hand of the small predators, into the gentle, browsing hand of the long-necked sauropodomorphs, into the prey-grasping claw of the early carnivores. Across the Carnian, in a window of perhaps a few million years, this body plan radiated. It did so quietly. There is no sudden burst in the fossil record of dinosaur dominance. What there is, instead, is a long, gradual rise, a slow filling in of the niches that the old fauna was leaving behind. The plant-eating sauropodomorphs grew larger, longer-necked, able to reach into the new conifer canopies. The early predators grew faster and longer-legged and better at chasing prey across soft ground. The herbivores split into smaller and larger forms. The first armored dinosaurs appeared, the first long-tailed runners. And in time, though not yet in the Carnian itself, these forms would become the great lineages of the Mesozoic, the sauropods of unimaginable size, their footsteps shaking the Jurassic, the theropods of which Tyrannosaurus would be a much later descendant. The ornithischians with their beaks and their armor and their eventual horns, the birds which were dinosaurs too, even now, hidden inside the early small forms. All of these futures were folded quietly into the Carnian forest in the bodies of small, watchful animals who knew nothing of what they were beginning. It is worth a moment in the long quiet of this reign to think about that. About the bird that lands today on a window ledge, the magpie, the sparrow, the gull above a coastline, and about the long, unbroken line of survival that connects it to a small bipedal reptile of no particular importance, walking through the wet undergrowth of southern Pangaea 230 million years ago. That bird, in some sense, has never stopped walking through the Carnian. The body that carries it through the modern air is built on the body that walked through the Carnian rain. The same is true of every other living thing. The mammals, even smaller than the early dinosaurs, kept their place in the New World too. They were quiet. They were nocturnal. They were not, then, anyone's main story. But they were there. The lineage that would eventually carry humans through the great extinction of the dinosaurs, through the long Cenozoic, and into the moment of this very narration, was already alive in the Carnian. It was already drinking from the slow rivers. It was already sleeping in the long, damp nights beneath the same long rain. There's a kind of stillness that comes from sitting with such a thought. The earliest mammals in this age were creatures perhaps the size of a shrew, perhaps a little larger. They lived in the leaf litter and the undergrowth. They ate insects and small reptiles and the eggs of larger animals when they could find them. They were warm-blooded, already at this early point generating their own heat from the food they ate. They had fur, they had whiskers. They had the small, rapid movements of animals that, in a world full of larger predators, must always be alert. For 230 million years, those small bodies have continued. The line has never broken. From the earliest mammals of the Carnian, through the burrowing survivors of the end Triassic extinction, through the small-bodied mammals of the long Mesozoic, through the rapid radiation that followed the death of the non-bird dinosaurs, through every primate ancestor in the long forests of the Cenozoic, the line has held. Every link, alive in its moment, eating, sleeping, breathing, mating, dying, passing on its inheritance to the next link. None of them knew that they were carrying anything. They were only living the way every creature only lives. And the listener tonight, lying still, is the next link. Whatever happens after, the long line continues, for a while at least, for as long as the body holds. The air drawn in this breath was, in its atoms, in the same atmosphere as the Carnian. The water drunk this evening was, in its atoms, the same water that fell in the long rain. None of this needs to be remembered. None of it asks to be honored. It is only quietly the fact of the body, that it belongs to a long line, and that the long line passes through it for a while, and that the planet, which has held every moment of that line, is holding this one too. After 2 million years, the rain began to ease. It did not stop suddenly. It slowed. The Wrangellia eruptions, which had pulsed and pulsed for so long, finally exhausted their main intensity. The carbon dioxide that had thickened the atmosphere began slowly to be drawn back out into the new forests, into the new soils, into the calcium carbonate of the recovering reefs. Over hundreds of thousands of years, the atmosphere returned closer to its pre-pluvial chemistry. The oceans cooled by a few degrees. The hydrological cycle quieted. The deserts in the heart of Pangaea did not return to their full former extent. The continent was already breaking, even now, beginning the long process that would eventually scatter its pieces across the modern globe. But the climate stabilized. The planet found a new, drier equilibrium. In the rocks, this change is read as a fading, not an ending. The gray, organic, rich layers thin. Red layers begin to reappear in places. Paleosols become drier, less continuous. The freshwater lakes shrink. The reefs, once flushed by river mud, return to clearer waters. The sediment record, which during the pluvial had been rich and detailed, becomes sparser again, less organic, less wet, less green. But the world that the rain left was not the world that the rain had found. The old reptiles of the dry Triassic, the rhynchosaurs, the dicynodonts of the open plains, many of the early archosaur lineages, were gone or much reduced. The reefs were rebuilt of new corals, the forests were full of new conifer species, the rivers settled again, ran through valleys whose shapes had been carved by the long pluvial floods. And inside this new post-rain world, the dinosaurs were the dominant lineage of large land animals, not yet at the immense scale of the Jurassic, but already on every continent, in every habitat, ready for the long age that the rest of the Mesozoic would give them. 2 million years of rain had cleared a path. It had not done so on purpose. The planet has no purposes. It has only physics and chemistry and the long, slow accident of mass in orbit and tectonic motion. The volcanoes opened beneath the sea. The atmosphere thickened. The rains came. The plants and animals that fit the new conditions thrived. The plants and animals that did not faded. And the world continued, unhurried, into its next chapter. It is a pattern that is played out in different forms throughout Earth's history. A change in the deep machinery of the planet, a volcanic province, a shift in ocean circulation, an asteroid, a continental rearrangement, and the surface, in time, reorganizes around it. The lives of every creature alive at that moment are gathered into the new arrangement. Some lineages end. The long inheritance of the planet continues on a slightly different course than it would have taken without the change. The Carnian Pluvial was one such turning, a small one in some ways, a vast one in others. 2 million years is not long in geological terms, but what came after it, which is to say, the entire age of the dinosaurs and everything that the dinosaurs made possible, is unimaginable without it. If the rain had not fallen, the dinosaurs might have remained a small lineage among many. The dicynodonts and the rhynchosaurs might have continued to dominate as they had for tens of millions of years. The Mesozoic, if it had unfolded at all in any recognizable form, would have looked very different. There would perhaps have been no sauropods of immense size, no tyrannosaurs, no long radiation of the small feathered ancestors of birds. The eventual end of the Cretaceous, 66 million years ago, might have ended a different caste of dominant animals, with different consequences for what survived and what did not. The mammals, which spent the long Mesozoic small and quiet beneath the dinosaurs, would have spent it small and quiet beneath some other set of giants. The forms that came afterwards, including, eventually, the primates and the apes, and the long line of human ancestors, would have evolved into a different world against a different ecological backdrop. Whether any of them would have evolved at all is impossible to say. What is clear is only the broad shape of how histories build. A change, somewhere deep in the earth, alters the surface conditions. The surface conditions, altered, shift the lineages that thrive. Those lineages, once established, set the framework for everything that comes afterwards. Layer upon layer, contingency upon contingency, the planet writes its long story, never the same twice, never reversible, always cumulative. The Carnian rain is one of those layers. It sits in the rocks of the Triassic, between the dryness below and the dryness that returned afterwards, and it holds inside it the quiet branching point at which the dinosaurs began their long claim on the world. Without the rain, no dinosaur lineage radiates as it did. Without the dinosaurs, the entire shape of the rest of life on Earth is different, and the Carnian rain itself happened because, far from any animal alive at the time, the ocean floor opened, the lava flowed, the carbon dioxide rose, and the air, once warmed, gathered more water than it could hold. The rocks of the Carnian rain are still here. If a person walks today through the Italian Dolomites in the mountains above Cortina, the limestones in the Dolomites tell their story openly. The lower layers are pale, hard, dry, the carbonate of the older Triassic Sea. Above them, a band of darker, mudstone-rich rock, the Heiligkreuz Formation in the older naming, records the long humidity of the pluvial. Above that, again, the carbonate returns. The rocks lie almost level in places, the way layers of rain lie in the sediment of a calm pool. In the Germanic Basin, beneath the modern fields of Central Europe, the same band exists, buried far underground. In the Newark Basin of the eastern United States, in the cliffs of the Bristol Channel in Britain, in the Ishigualasto Formation of Argentina, the same change in color, the same shift in chemistry, the same long, soft band of mud appears again and again. The whole planet remembers quietly. The rocks have not forgotten. It took geologists over a century to understand what they were looking at. The first descriptions of the changed sediment in the late 19th century were local. A wet interval, an odd horizon, a curiosity. Only in the last few decades, with isotope chemistry, with global correlation of fossil records, with refined dating of the Wrangellia volcanic province, did the picture come together. In a very real sense, the Carnian Pluvial Event is one of the youngest of geology's old stories. It has been alive in the rock the entire time. It only began recently to be heard. The naming itself came slowly. In the early 20th century, Italian geologists working in the Dolomites used the name Rabel after a small alpine valley for the dark, mud-rich sediment they had begun to recognize as anomalous. The name stuck for a long time in regional usage. Other geologists working in Britain used different names. The Murcia Mudstone Group, the Bristol Beds, with their own local terminology. In Germany, the layer received its own designation. In Argentina, in the Ishigualasto Formation, the same change in color and chemistry was noted, but described in terms of the local rock units. For decades, no one realized that all of these local horizons scattered across the continents were the same horizon. They were one event in a single planetary atmosphere, recorded everywhere on Earth. The unification of these local stories into a single global event was the work of careful comparison. Carbon and oxygen isotopes were measured in carbonate rocks from continent after continent. The dates of the Wrangellia basalts were refined by uranium-lead chronology to an accuracy of a few 100,000 years, a precision that, for rocks 230 million years old, is itself a quiet wonder. The fossil record of the dinosaur radiation was matched layer by layer with the climatic signal in the surrounding rocks. The signal, once compared, was clear. From around 234 million years ago to around 232 million years ago, the world had been wet, almost everywhere, in a way it had not been before and would not be afterwards. The story now lives in the textbooks. It lives in research papers, in conference talks, in the long, careful patience of scientists who, generation after generation, work the same outcrops, refine the same dates, return to the same questions, and gradually deepen the picture. The Carnian, which had been almost invisible a century ago, is now one of the better understood intervals of the Triassic. It is, in the slow accumulation of human knowledge, becoming as ordinary a chapter as the great extinctions, the long Jurassic, the rise of the mammals after the dinosaurs. It has been brought gently into the long story that humans tell themselves about where they have come from. To hear it now, with whatever stillness this evening allows, is to be told very softly that the world is older than any of its present moments, that the conditions of the present are not eternal, but neither are they accidents, that a single shift deep beneath the ocean in a place no one would later name became a rain that became a forest, that became a lineage, that became, in the long final reach of time, every animal alive on Earth today. There is no message in this. There is no warning. There is no urgency. The Carnian rain was not a lesson. It was a length of weather. It happened. It ended. It left behind a world. And in that world, eventually, some of its descendants learned to walk on two legs and to look at rocks and to read the long story written there and to tell it back in slow, soft narrations to other descendants, lying still in the dark, thinking gently of a planet that has held so many ages of weather and that holds even now the listener. The night is quiet. 230 million years are quieter still. Beneath every word of this telling, the long Carnian rain is still falling, somewhere in the deep memory of the rocks. It will keep falling in that memory for as long as the rocks remain, which is to say, for far longer than any listener tonight will need. There is nothing more to keep, nothing more to track. The rain has ended, the forests have grown, the lineages have walked their long way forward, the dinosaurs have come and gone, and their descendants, small, feathered, asleep in trees somewhere in the dark of this same night, carry the old line forward without thinking of it. The planet beneath the listener is the same planet that held the Carnian. The atoms that pass through the body in this breath and the next have been here through every age. They have lived in the dry plains of Pangaea. They have lived in the long rain. They have lived in the bones of the first dinosaurs, in the leaves of the first conifers, in the deep mud of the first wet lakes. They are old in a way that has nothing to do with the body that carries them now. There is no reason to hold on to any of this. No image needs to be remembered. No fact needs to be saved. The story will keep being there, in the rocks, in the long silence of the earth, with or without anyone hearing it. Its only request tonight has been a little attention, and even that now can be released. Let the rain continue somewhere beneath the centuries. Let the forests grow somewhere in the soft dark. Let the breath slow in time with the long, slow weather of a planet that has always been calm, even at its strangest. The Carnian rain has been falling for 230 million years already, in one form or another. It will fall, in memory, a little longer. There is no need to listen any further, only rest now. The world, as it has always done, will keep its own time.